In the last few videos, we've spent quite a bit of time developing the idea behind first the slope of the tangent line, and then subsequently this idea of a derived function, which we call the derivative, from which we can find the slope of the tangent line. And we worked through several examples that involved quite a bit of work, quite a bit of algebra because we're relying on this particular limit. And as much fun as that process is, it's not the most efficient way to find a derivative. So what we're going to do, starting with this video, and then a bunch of other videos to come, we're going to develop some rules or techniques with which, based on the type of function that we see or that we have to find the derivative of, we can apply one or multiple rules in order to get the answer, right? So before we jump right into the first set of rules, we're going to say a little bit more about one of the words in this title, differentiation, right? This is the first time, pretty sure this is the first time I've used this word. So differentiation, right, is the process by which we find the derivative, right, of a differentiable function. So assuming that the function has a derivative, the process by which we find that derivative is called differentiation, right? And so we have a function here. And so yeah, let me just kind of write down something generic. So we have our function, and right now we have this limit, right? So the limit as h approaches 0 of our difference quotient, right? We have that particular process that leads to the derivative, which we denote like this. And then I also mentioned there is this notation that can be used for the derivative, and this is called the Leibniz notation, and this is called the prime notation, right? So we've pretty much been on this arrow, since we started talking about slopes of tangent lines and instantaneous rates of change. But now what we're going to do is develop another path, right? And actually, maybe what I should do is have this other path that ends up, so maybe I'll do it arced like this, where instead of relying on the limit, we're going to have certain rules and or techniques, whatever you want to call them, right? That will take us to the same conclusion, but again, hopefully with a lot more efficiency, right? So on one hand, we can use the limit, and then on the other hand, we're going to develop some rules. Now, these are not like completely separate. In order to come up with these rules, we are going to make reference to this limit over and over and over again, right? So it is meant to emphasize the importance of the limit definition of the derivative. In other words, we've seen how it works, but now we're going to use it in such a way that we can develop certain rules that will make the more practical approach of finding a derivative much more efficient, right? So we don't have to spend much time using algebra in this sense. We might have to use algebra in a different way as far as rules are concerned, but it won't involve us computing a limit every single time we have to compute a derivative, right? So differentiation, think of it as a verb. It is an action word. It is something that you do. And once that action is done correctly, the end result is the derivative. All right? So, so we have a few kind of basic results to get to, and then there are a couple of really big ones that we want to get to. So let's get started. So the first one deals with the simplest type of function, right? And what is the simplest type of function? Well, it's a function that's a constant. So like if you graph it, all you see is a horizontal line. It doesn't go up, it doesn't go down, it never changes. Hence, we call it a constant, right? So this is going to be called the constant rule, right? And every rule is going to have a name. And its name is going to be based on some kind of algebraic property, or something that has to do with algebra. The language of calculus is algebra. If you're good at understanding that language, then you're one step ahead of the game as far as understanding how and when to do all the things that calculus will ask you to do. All right. So the constant rule. So what I'm going to do, instead of like stating the result in a formal proof, I'm just going to say, okay, I'm going to start with the proof and then summarize at the end, maybe in a different color, get all fancy, and say, okay, this is the result that we just derived, right? So again, we're going to use the limit a lot, but after we've used the limit for certain types of functions and we know the pattern, we can turn that pattern into a rule, which we can hopefully apply a lot more effectively, right? So let's say, so what do constant functions look like? Well, it's something like y equals c, where c is any real number. So let's set up our difference quotient, right? So what I will do is I'll use the D notation here. Since we've used the prime notation a lot, let's kind of balance it out and get used to the other notation as well. And for now, it's still a limit, right? But not for long, because we're going to figure stuff out. So we have our constant function, and now we have to first simplify this difference quotient like we've done in every other problem up to this point, and then compute the limit. Well, for a constant function, since there is no x to plug in, then for all values of x, this is equal to c, and so is this, right? In other words, because there's no x to replace in a constant function, the f of x plus h is equal to c, and so is f of x, because no matter what I plug in here, that function will return a constant value. Similarly there. So in the numerator, like everything cancels out. Now isn't that wonderful? When you think of the other numerators that we've dealt with, everything didn't cancel out, right? In fact, we were left with sometimes really complicated expressions. But now we have this, so the limit as h approaches 0 of c minus c, which is 0 over h. Now, this is sometimes confusing for students because what they try to do is plug in 0 and then they'll get 0 over 0. But pretend for a second that the limit isn't there, and I ask you to simplify this even further. This is not in its most reduced form, right? Because even though h might be small, right, it's approaching 0. It's never actually equal to 0. But the numerator is equal to 0. So if I have a fraction where there's a 0 in the denominator and something small, 0 in the numerator and something small in the denominator, then that fraction simplifies to 0. So we end up having the limit as h approaches 0 of 0, which is a constant, so we end up with 0, right? So now let's summarize it. So if our function is a constant function, then its derivative is 0, right? So let's do the summary like in a different color and say if y is equal to c, a constant, then its derivative is always equal to 0, right? So there we go. Now, granted, how many times are we going to have to work with a function that's just a constant? Probably never. But constants might be a part of other functions. So it might not be a constant by itself, but maybe it has a constant in there, like a x squared plus 2 or e to the x plus 10. At least we know how to differentiate the constant part. The question is, what do we do with the other parts? Well, glad you asked, because or I guess I asked, but the thing is, we're going to develop rules for that. Now, before we get to those rules, our next theorem is a really big one, and it's called the power rule, right? So here's our theorem. It's called a power rule, right? And what it says is it's going to give us a very, very useful rule that will apply in many instances. Unlike the constant rule, where you'll probably never just get a problem that involves finding the derivative of just a constant, right? But let's look at this type of function. Now, what do we mean by power? Well, going back to algebra, a power function is where your x is raised to a constant power, right? So your x is raised to a constant power. So n is some real number. Usually, I mean, it could be 0. If n is equal to 0, then this function would end up being just a constant. So it would simplify to this, which we already know how to differentiate, right? So this is a power function. And what we're going to do is we're going to, again, use our limit definition to come up with a rule for finding this derivative. Now, when we go through the process, I'm going to use a result from algebra called the binomial theorem, and it's a very important theorem, and I don't know if you've been exposed to it. So maybe there's going to be a step in this process that looks a little strange to you, but I'll point out exactly where that step is and tell you that, again, it's based on the binomial theorem. Now, the binomial theorem in its own right is another big theorem that I certainly don't have the time to prove. It would require a process that's called mathematical induction, which again is not a part of our course at all, right? So you're just going to have to trust that theorem works. And if you're interested, certainly Google the binomial theorem and you might see how it's used. It's helpful when you have to expand things like a plus b squared or a plus b cubed or to the 4th power or so forth, right? Okay, so let's write it down. So our dy dx again will be the limit as h approaches 0, again, of f of x plus h minus f of x over h. So now here is my f of x, right? So now I actually have an x in there that I'll have to replace with the quantity x plus h. So let's write down that next step. So the limit as h approaches 0 of x plus h raised to the nth power minus x to the nth power all over h. Now, the reason why we need this special result from algebra is because I don't know what the power is. Is it 2? Is it 3? Is it 1,000? I don't know. So I can't say, okay, we're gonna like FOIL it out this many times because I don't know how many times that would be, right? But the binomial theorem, it gives us a way to expand powers like this, right? Or binomials like this for any n, right? And that's why it looks a little messy. So here we go. So I'm going to start a little further to the left. Here's our limit. And so it turns out when we expand this part, we are going to get an expression that looks like this. The first term is going to be x to the n. And then the second term is going to be n times x to the n minus 1, and then times h, right? And then the next term is going to be n times n minus 1 over 2, and then this is times x to the n minus 2, and then times h squared, right? And then what I'll do is I'll write down one more term so you kind of see the pattern, and then you're going to have plus n times n minus 1 times n minus 2 over 6. Right? Now the 6 is a little mysterious where it comes from, but again it comes from that formula, and then you'll have x to the n minus 3. Right? So you'll have x to the n minus 3 times h to the third power. And then this pattern is going to go on dot, dot, dot until what we're going to end up with is this. We're going to end up with n times x times h to the power n minus 1. And then finally plus h to the power n. So all of that, right, is the expansion of x plus h to the n. It looks like a mess, but again, we have to rely on a formula like this simply because we don't know what the n is. And then from that, I have to subtract x to the n, so just minus x to the n, so that's this term, and then this is all over h. All right, so again, as I said, I will highlight the part here. So this is due to what we call the binomial theorem. Right? Now, if you look closely in the numerator, the x to the n that we have right here is going to cancel out because we have a minus x to the n right here, right? So that goes away, and then everything I have left, and we've seen this before, everything we have left has an h in it. At least we have like h to the first power, h to the second, h to the third, and then all the way up to h to the nth power. So because of that, like when we were dealing with those polynomials, we were able to factor an h out of the numerator. We can do that right now. So let's take an h out of the numerator. So take out the h, and then in square brackets, I'm left with, for the first term, I just have an n times x to the n minus 1, and then plus. If I take out an h out of this term, I'll just have an h left, right? Because I have an h squared there. I'm going to factor out 1h, so that means I have to subtract 1 from this exponent. So then I have n times n minus 1 over 2 times x to the n minus 2 times h. When I take out an h out of this term, again, I have to subtract 1 from that exponent. So that h cubed becomes an h squared when I factor out that h. So I have this, and then that, and then over 6. and then we have x to the n minus 3, and then times h squared, right? And then that pattern will continue. Let's see, so now when I take out an h from the second to last term, just like I had to do with all the other powers here, I had to subtract 1, right? When I subtract 1 from this power, I have h to the 0, which just works out to be 1. If I subtract 1 from this power, it becomes h to the first power. If I subtract 1 from this power, it becomes h squared. If I subtract 1 from n minus 1, I'm going to have h to the n minus 2. So the n is still there, and then we have an x, and then we have h to the n minus 2. And then finally, when I factor out an h from this term, again, I have to subtract 1 from that exponent. So I have h to the n minus 1. And all of that is in square brackets. And this is all over h. But the beauty of this now is that we have a common factor of h. So this h and this h reduces my fraction. All right? So we're almost there. And then we can take a little yoga break. But we have the limit as h approaches 0. In square brackets, I have n times x to the n minus 1 plus n times the quantity n minus 1 over 2 times x to the n minus 2 times h plus n times n minus 1 times n minus 2 over 6 times x to the n minus 3 times h squared plus dot 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 plus nx h to the n minus 2 plus h to the n minus 1. And now we get to evaluate this. You might be thinking, what? How am I going to do that? Well, take a look. All but one of the terms in this expansion, right? All of them except for the first one has an h, right? This has an h, this has an h squared. All the stuff in here would have like h to the third, h to the fourth, all the way up to, again, this h to the, and it could be a huge number there, right? So if I plug in 0 there, 0 there, 0 everywhere, including there and there, all those terms are equal to 0 because they're all being multiplied by either 0 or 0 raised to some power, which is still 0. So all that mess, it just goes away. And we love it when messes go away. So this is the limit as h approaches 0 of just this. N times x to the n minus 1. But this now doesn't involve h at all, right? In fact, we don't even really need to write the limit anymore, right? And that's what our derivative is of our power function. So all this mess, like, can you just imagine the first time someone, came up with this proof? They're like, really? This is what I have to work with? And then all of a sudden, terms just fall out, and all you're left with is this really, really simple expression, right? So here's our summary, right? So if we have one of our power functions, so where we have our variable raised to the power, some constant power, then when I do that limit, no matter what the power is, whether it's 2 or 2 million, it will end up being this. Seems like that power comes down, so you have n times, and then you have your variable x, and then it's raised to n minus 1. And this is the famous power rule, right? So from now on, whenever we have an x raised to a constant power, let me emphasize that it has to be a constant, right? So n constant. Once we have that, then we can always use this rule and write down what the derivative is, right? And what we're doing in this video, I am establishing a certain set of really basic rules. These are all very easy rules. And then at the end, we'll do a couple example that utilizes all of them. And you'll see just how having these rules make things so much easier. All right? All right, so let's look at just two more that we have to do, and they're relatively easy. So we've looked at the constant function, and we've looked at the power function. We have actually three more results to go. And the very last one, I'm not going to prove it now. We will kind of look at a proof later. But this theorem is called the constant multiple rule. Right? Constant multiple rule. What do we mean by constant multiple rule? Well, here, when you see a phrase like constant multiple, it says you have a constant that's multiplying something, right? So now, the next couple of rules, right? This one and the next one, these are more general. That would work for any type of differentiable function, as long as it reflects this particular type of operation. So what do we mean by constant multiple? That means whenever you have a constant multiplying a function, right? Because we've seen this a lot. You know, sometimes you don't just have like an x squared. You might have a 4x squared, or a 10x squared, or a 1/2 x to the third power, or something like that. So you could have a constant multiplying your function, right? And again, this rule that we're going to establish will work whatever the constant may be, right? That's the beauty of theorems and properties. And so as long as, you know, certain conditions are met, then they always work, right? You know, we love that about math, things that will always work. And what I'm showing here, I'm not just, I could spend 5 minutes and just write down the rules, and you're like, really? Is that it? But I want you to see where these rules come from and how important the limit definition is in establishing these rules. All right. So let's see if we wanted to write down the derivative or compute the derivative of this. Right. So this will be the limit as h approaches 0. Again, let me write down the general thing. Like I said, we're going to write this a lot, right? But once we do this now and we come up with these rules, suddenly the limit will kind of fade into the background, and the rules and the techniques will become at the forefront, right? So how does this work when we don't even have a specific type of function, right? Well, let's see. Let's see what algebra can help us and do. So, for instance, here, it's basically saying take this function and wherever there's an x, replace it with x plus h, right? So the constant is going to be multiplied, is going to be multiplying, I should say, f of x plus h. So I'll have c times f of x plus h like that. And then the minus, well, the function itself is just this, right? Like this is my function. It's a constant times it, right? So the constant will be there as well, right? And then this is all over h. So, you know, what can we do with this? Well, I look in the numerator and I see that there's a common factor of the constant c. So let's factor out the constant out of the numerator, right? So it looks like this. So this is the limit as h approaches 0. And let me write this as c over 1 times, and then I have my difference quotient there, the f of x plus h minus f of x all over h. And just for emphasis, let me put a pair of brackets around that to say, okay, yeah, let's factor out the c, out of the numerator, and I just put it over 1 here as emphasis, right? So if we now, so we have this product here. And remember, we have a property for limits that says provided the limits exist, right? I can take the limit of this part and then the limit of this part separately and multiply the results. So I can write that single limit as the limit as h approaches 0 of c times the limit of my difference quotient, right? But c is a constant, and we know the limit of a constant is a constant. And then this part is, by definition, as long as our function is differentiable, well, this is going to be f prime of x, right? Well, so what did we just do there? Well, where was the sleight of hand? Well, there's no sleight of hand. What it's saying is, in fact, let me write down the summary for this one, and while I write it down, I'll verbalize what it's saying. So it is saying if you have a function that is a constant times a differentiable function, then that derivative is simply the constant times the derivative of f of x. So multiplying a function by a constant doesn't affect differentiation. Basically, that constant multiple just comes down and is now a multiple of the derivative, right? And this is helpful, and you'll see when we get to utilize all of these together, you'll see just how important this one is. Again, and this is one that you end up using multiple times, all right? Okay, hopefully you're still in there hanging on with me. So now we have another, like a pair of results that go together. I'm just going to prove one part, right? So here's our other theorem. And this is called the sum and difference rules. Again, notice these are words from algebra. We have constant, we have power, we have constant multiple, and now we have sum and difference, right? Again, all algebraic words, right? So this is our theorem. And basically, so I'm going to prove the sum part and just explain why the difference part is almost identical. And maybe what I'll do is just leave it as a little exercise for you to do on your own. And then maybe you'll get some reward for doing it, because I'm just that kind of person. Okay, so let's look at the sum. So what this means is, it's saying suppose your function is not just like one term, but what if there is another term? So what if it's like this? You have like one function added to another function. And let's assume that these two are differentiable. So let's say where f and g are already differentiable. So the question is, what happens when I add them together, right? Well, let's see. If I want to find the derivative of this new function, which is f plus g, so let's write it down. So dy dx is the limit as h approaches 0 of... Now, so I'm going to write this one a little bit different because I have f and g here. So it's like, there are two terms. What I'm going to say is I'm going to use this letter, so y of x plus h minus y of x, and then over h. So instead of using, now when we had just one function, like, just one term, right, we could have used either one. So I just opted for the f. But now since we have not just an f, but we also have a g here. I'm going to use this because I want to represent the sum of both of these terms. So I can't just say f of x plus h, because then I would just be working with this. I need to work with the entire sum, hence I'm using the y notation here. But it's still our same difference quotient. Okay, so now how does this one work out? Again, when we don't know what f is and what g is, well, I mean, we can still write it down symbolically, right? That's the idea behind a proof, right? So this part is saying wherever there's an x, replace it with x plus h. So I'm going to have f of x plus h plus g of x plus h, right? So that's the first term in the numerator, and then the second term in the numerator, I have to subtract the f of x plus g of x. So like this. And then this is all over h, right? Well, what can we do? So, well, this is where we'll do a little bit of algebra with fractions, and just kind of, so what I'm going to do, I'm going to collect the terms in the numerator that have the f to them. So I notice there's an f of x plus h, and then there's a minus f of x. So I'm going to collect those together. So collect all the f's together like this, and then collect all the g's together, right? Now this is a plus, so I'm going to write it as plus g of x plus h, and then when I distribute this negative to this g, I'll get a minus g of x, right? And this is all over h. However, since I have just what I can do is, instead of thinking of it as one big fraction, I can write this as this term over h plus this term over h, and then take the limit of that sum, right? But we have a limit property, again, that says if I know that the individual limits exist, I can find the limit of the sum by taking the limit of the individual terms. So I can take the limit as h approaches 0 of f of x plus h minus f of x all over h plus my limit as h approaches 0 of g of x plus h minus g of x all over h. But what are those? These are the definitions of f prime of x and g prime of x. So this is equal to f prime of x plus g prime of x. How is this helpful? Let me write down the summary and you'll see what we've just shown. So if our function now has multiple terms, more than one, so if our function looks like this, f of x plus g of x, what we've shown, so then to find the derivative of a function that has multiple terms, what this is saying, just take the derivative of the first term, so this will be f prime of x, and then keep the plus sign, so that plus sign there, that plus sign there, here is the same plus sign, so it's f prime of x plus g prime of x. So if we were to say this out in words, it says if I have to take the derivative of a sum, it's the sum of the derivatives, right? And it turns out it works exactly the same way for the subtraction. So that's why they're grouped together. So I'll put that as a part of the summary, but then I will just say, if you would like to replicate and that you can follow this proof very, very closely, the only difference is you're going to have a minus in here and a minus in there, and you'll just have to do a slightly, just ever so slightly, a different, a little bit different algebra. But if you have the difference, then the derivative of that difference is f prime of x minus g prime of x. And these are the famous, they're famous in the mathematical community, and they're about to be famous for you because you're going to use them over and over and over again. But these are the sum and difference rules. All right. So again, let's recap: constant, power, constant multiple, and now sum and difference. Right. Now there's another rule that I am going to. I often wonder, like, when is the best time to introduce this particular one, and it is one for the exponential function, the special exponential function e to the x. So this is, I'm going to say, our natural exponential, meaning base e, right? So natural exponential rule. Now you may have not described it as the natural exponential, but the reason I'm doing that is I want you to think of it and its relationship with the natural logarithm. So there's a natural logarithm and its exponential equivalent. I just like to call it the natural exponential because they both use base e. All right? So what I'm going to do is give you a sketch proof of that. I'm not going to give you the full because this would almost double. Like the proof of this one would be longer than all the previous proofs that I just did. All right. So, but this is the type of function that we are looking at: e to the x. Right. Okay. Well, let me at least set it up and walk you through, and I'll say where am I going to like skip all the details because there are a lot of details that go into that step. But if we want to find the derivative, so dy dx is equal to, again, it's our function evaluated at x plus h minus our function over h, right? Well, let's set this up. Now, this is a little bit different than our power function. Do you notice the difference between the exponential and the power? Now, your variable is in the exponent and your base is a constant. Remember, e is that number 2.7191 and so forth, that nice irrational number. Well, now that my variable is in the exponent, this is where I'll have to put x plus h. So this is going to be e to the x plus h minus e to the x all over h. Now, what can I do with this, right? Well, what I can do, the e to the x plus h, I can factor that using my properties of exponents as e to the x times e to the h. So I could do that, right? So we have, so yeah, write the first term as e to the x times e to the h minus e to the x all over h. How does that help? Well, now I have an e to the x as a common factor in the numerator. Factor out e to the x. So, and I'm gonna do a very similar process to what we did when we did the proof for the constant. So factor out the e to the x. I'm gonna put it over 1. And then what's left now is e to the h minus 1 over h. And I'll put that in square brackets just like I did before, right? And it's another product. We're taking the limit of a product. So what am I allowed to do? I'm allowed to take the limit of the separate factors. So I can take the limit as h approaches 0 of e to the x times the limit as h approaches 0 of what I have in square brackets, which I technically don't need to write the square brackets anymore, but I've already done so. Right. Now, this part here, even though the e to the x is not a constant, because it's not a constant function, but it doesn't involve h anymore, right? So this doesn't involve h, so as h approaches 0, this is not going to change. It's still going to be e to the x. So the first factor has a limit That comes out to be e to the x. And then what about this other part now? This is the difficult part. And it turns out, and I do actually encourage you, like if you were to set up a table of values, let's say as h is getting very, very small. So numbers like 0.1, 0.01, 0.001, and do the same thing on the negative side. So the two one-sided limits. If you did that with this, you would come up with an estimate that the limit appears to be 1. And that's exactly true. This limit that we have of e to the h minus 1 over h, that limit is equal to 1. And that's the step that if I were to show you why it's really equal to 1, like algebraically, it will take a long time, right? So this is where you'll have to take my word for it. And so what do we have left? E to the x times 1. So this is e to the x. That is pretty remarkable because that's the function we started with. We started with e to the x. We do our differentiation process through the limit, and the result is still e to the x, right? So here's our summary of our final one. So if our function is our special e to the x function, then its derivative is known to be e to the x, right? Really, really important property here. Very useful. And think of it about this as a rule. I mean, it doesn't get much easier than this. Maybe the constant rule is easier than this. But the derivative of e to the x is itself. All right? So there we go. We have now a really good list of rules to start building this calculus mansion, this skyscraper that's going to represent lots of important results, and we'll be able to solve lots of really cool problems. But it starts with this process, knowing the rules, knowing how to apply them. And what I'm going to do in the next video is just do some examples, lots of examples, illustrating how we use these rules, and you'll see just how efficient the rules are as opposed to always going back to the limit, right? So the idea is we use the limit, come up with these rules, and then we can rely on the rules going forward. All right, so hopefully you're ready to take that journey with me. See you then.